Thank you, everyone, for tuning in, and thank you, Zoom, for hosting this session where we discuss building on top of AWS services for in-meeting Zoom experiences. Before we get started, I just want to make a note on the material that we're covering here today are for information purposes, and want to make note of the safe harbor statement. Today, we have myself. I'm Sina Sajudi, Principal Solutions Architect with AWS, and I focus on ISV accounts. I'm going to pass it to my co-presenters, Chris.
Hey everyone, my name is Chris Lott. I'm also a Solutions Architect here at AWS, and I focus on our language AI services. John?
Hi, I'm John Slominski. I'm a Principal Solutions Architect from the AWS Prototyping Organization. I'm focused on application development, DevOps, and event-driven architectures. Back to you, Sina.
With all the buzz going on with AI, particularly in natural language processing and computer vision, I am so excited to be speaking with you about the joint collaboration between Zoom and AWS. Developers are eager to build next-generation communication and business productivity solutions with the Zoom platform. Over the past year working together, we have come across a number of use cases that we can accelerate development and time to market for the developer community. There are tremendous opportunities for startup, enterprise, and public sector developers to build agent assist, live translation, visual content moderation, identity verification, and other AI productivity apps. Today, my colleagues and I will talk about how Zoom and AWS teams are making this journey easier for developers. You will learn how to stream Zoom meeting participant audio and video live to AWS, and we'll give you an example of the type of AI solutions that you can build yourself. I want to start with a story about one of these use cases a year ago. AWS Prototype and Cloud Engineering Solutions Architects and the Zoom R&D team collaborated on a live speech translation prototype. The architecture was simple. Pipe mixed audio from a Zoom desktop client to Amazon Transcribe for live transcription, stream the transcriptions to Amazon Translate, receive translations from many of the supported languages, and convert the text back to speech using Amazon Poly. The results were impressive. You could listen to the voice of the virtual translator live in Mandarin, while the original speaker spoke English with 1 to 3 seconds delay. But no journey is without its challenges. And we noticed this most when we were discussing operationalization. You see, packaging a desktop app to run as an executable in the cloud is virtually impractical. For one, manual interaction with the UI is not possible. Even with a headless application, orchestrating a fleet of virtual participants running a desktop app is inefficient and cumbersome. Finally, most use cases we considered required access to per participant audio, not the mixed audio captured by an audio driver. As we dove deeper, we recognized the need for a joint investment if we wanted our developers to be successful. In addition to helping developers operate virtual participants at scale, we had to address the complexity of point-to-point integration with AWS and third-party services. These were ultimately going to be the applications which consume live audio and video from Zoom meeting participants and provide value to the end users. Working with customers and developers, we knew there must be a better way. We set ourselves up for a challenge with Zoom to create serverless architecture and sample solution on AWS. We kept 3 goals in mind to really help developers. First was removing as much friction as possible for the developers so you can get products shipped to market as fast as possible. Next was ease of operations. It doesn't matter how fast you can build it. If you can't run and maintain it at scale, you can't really deliver value to your customers. And lastly was cost efficiency. We were very conscious of the feedback from the developer community on this. If the solution is not economical, it will never see the light of day. We believe this architecture and reference solution can set you on your way to build great Zoom applications and successfully run them on AWS. Today, I'm really excited to announce the open source release of the AWS Virtual Participant Framework for Zoom meetings. This is an Apache 2 licensed sample solution hosted on GitHub as a part of AWS Samples. We're looking for the developer community to test it out and contribute to the open source sample. You will need an admin access to your dev environment AWS account. And you also will need to register for a developer account on the Zoom app marketplace so that you can get access to the SDK and the APIs. Let's talk about how we got here and the design steps we took to evolve a desktop-centric prototype into the cloud-native architecture solution that we're releasing today. Step one was to programmatically gain access to Zoom meeting, audio and video, and integrate the custom app with AWS client libraries, specifically Amazon Kinesis video stream for audio and video data transfer, and Amazon Simple Notification Service for signaling and event processing. We built the virtual participant framework on top of Zoom Meeting Windows SDK. The Windows SDK is essential because it provides access to high quality per participant audio and video using subscriber callbacks. This enabled a more robust solution compared to tapping into multimedia using audio driver and screen capture of a desktop client running on Mac or Windows. First, we made it easy to send raw audio and video to AWS. The sample implementation uses GStreamer media pipelining library written in C++ to stream audio data from Zoom Meeting SDK to Amazon Kinesis video stream. We will go deeper into why we chose Amazon Kinesis video stream later in this talk. Second, we made the Zoom SDK application headless, so it doesn't depend on manual UI interventions to join and leave meetings. There's a micro web framework for C++ called CroCPP, which exposes join, leave, and health web endpoints on port 3000. Lastly, we incorporated Amazon Simple Notification Service SDK for signaling to consumers, which also can be used to send virtual participant fleet orchestrators lifecycle events to indicate when one is free to join or when it's experiencing a problem. The combination of the libraries, the application, and the integration is what we call the virtual participant framework. Let's look back at our design goals: agility, better operation, and cost efficiency. We'd love to hear from you and get your contributions and improve on this. But first, what we had to do was use Zoom Meeting Windows SDK sample solution to connect meetings with AWS. Two, we relied on web endpoints for interaction with the virtual participant and Amazon's Simple Notification Services for signaling to avoid that manual intervention. And three, we minimized the developer time using the utilities provided by the Zoom platform and AWS SDKs. Let's talk about how you can scale your virtual participants in the cloud. Running and scaling a fleet of desktop applications is inefficient, costly, and complex. We know of startups and enterprise organizations who are doing this today, but even they are rightfully discontent with the status quo. Surely there's a better way. And thankfully, AWS and Zoom know a thing or two about running workloads at hyperscale. Once again, we borrowed from our joint experiences to make this easier for our developers. Modern DevOps has provided a great way to run custom applications that scale in the cloud. Containerization has become a standard practice to create reproducible artifacts that run the same in development, pre-production, and production environments. So we took it on ourselves to package the Zoom Meeting Windows SDK sample and all of its dependencies as a Docker image, a Windows Docker image to be specific. Now you can run them on your local desktop and in the cloud, knowing that it will run the same business logic. Here are a set of AWS services that can help you operationalize deploying and running containerized virtual applications. The first step, naturally, is to package the Zoom application as an executable and using Docker files to convert it into a Docker image. Next, you will need to register this image with a container registry. In this solution, we're using Amazon Elastic Container Registry or Amazon ECR as the Docker registry, which will integrate with the orchestrator of the containers. Now, when it comes to runtime, we're using Amazon Elastic Container Service, which orchestrates the Docker images, scales them out, connects them to network and dependencies so that they can run as an executable. And to provide compute infrastructure, we're using AWS Fargate, which is a serverless offering from AWS that right-sizes a compute environment without the developer having to spin up their own EC2 instances. And finally, in order to run these reliably, you can use Amazon CloudWatch as the observability tool, which can also act as a custom metric provider for autoscaling. And lastly, speaking of autoscaling, you can use AWS Autoscaling, which integrates with AWS, with Amazon ECS, and helps it to scale these virtual participant containers when there's high demand and to scale them down when they need to be wind down. Let's look at what drove our decision towards containerization again. We wanted to run the same reproducible application as a container in dev and prod environments. We wanted to operate virtual participants with auto-scaling and familiar DevOps practices. And finally, we wanted to optimize resource utilization for performance and cost efficiency. Now, the last step, we wanted to standardize on a single protocol, including the media container definition and encoding, to send Zoom meeting audio and video to AWS. And this way, that can be shared across a number of downstream services, including AI/ML services from AWS. We all know point-to-point integration is inefficient and grows exponentially in complexity. On the other hand, breadth of capability, choice, and flexibility are some of the core advantages of the cloud. We wanted developers to retain choice and keep it simple. That meant defining a standard media streaming protocol, purpose-built for downstream audio and video processing. So what's better than writing a lot of C++ on Windows point-to-point integration code? Defining a standard integration using Amazon Kinesis Video Stream, or KVS for short. And writing a sample to show you how you can integrate Zoom SDK and the KVS producer library. Amazon Kinesis Video Stream, or KVS, is a multimedia data ingestion, integration, and storage service on AWS. It's serverless and belongs to the AWS IoT service portfolio. You can use it to ingest audio data, video data, or a combination of both, or really any timestamp unstructured live data stream. KVS uses the Matroska multimedia container, also known as MKV, to package audio and video frames and metadata for transmission. The GStreamer library that I mentioned earlier helps capture audio and video from Zoom SDK callbacks and sends the multimedia data as KVS fragments to the cloud. Here's how the integration evolves now using KVS. You can see that the producer and consumer of the live media data are completely decoupled. And on the consumer side, AWS Lambda functions can be invoked to parse and integrate with AWS AI/ML services or really any third-party APIs. And this doesn't require a long-running WebRTC custom app or a media pipelining on the consumer side for that integration to happen. So really, the data, once it's in KVS, is available to be used for analysis and AI/ML solutions. I'd like to walk you through a simplified data flow. The first thing you need to do as a developer is set up the framework, which includes the Zoom Meeting SDK, Windows app, and the live media ingestion pipeline. Second, the Zoom app is going to send data to KVS service via the KVS producer library. One or more Lambda functions now will parse the data fragments from KVS, and the Lambda function sends the data downstream to AI/ML services by AWS or third parties. In the release sample, we have implemented an end-to-end solution that processes audio from Zoom meetings and sends it to Amazon Transcribe. It performs real-time speech transcription, and we will show you this in the demo. With community contribution, we hope to make more integrations available to you in the future. Now, let's look at what steered us towards this design. We wanted developers to build and integrate faster with flexible choices of programming languages. And this is all the languages that Lambda supports or a custom application that you can run as a container on the consumer side. We wanted the developers to be able to leverage existing AI multi-reference solutions built by the AWS dev community, either for KVS use cases or independently, any AI ML solution that's built for processing images, videos, or live text or audio can be plugged into the solution. Next, we wanted to reduce the operation and maintenance toil with a serverless architecture. And last, we wanted an auto-scaled live media processing to be based on load and for you to be able to pay for it as you go, as opposed to provisioning a lot of capacity. Okay, it's demo time. The first demo demonstrates Zoom's meeting that was transcribed using the sample solution we have released. In this demo, the Zoom SDK sample application streams participant audio to Amazon KVS, and the consumer is about 600 lines of JavaScript that reads audio from KVS and transcribed it using Amazon Transcribe. A particular highlight that I want you to note in this demo is showing the same SDK application and logic running on a standard Windows machine, which represents my local environment, and also noticing that it also runs on Amazon ECS on AWS Fargate, which would represent a production environment. This was important for us to showcase because it shows the very reason why Docker and containers have gained so much popularity with developers and DevOps practitioners.
Great. In this first demo, what I'd like to show you is a dual environment, one in my development and one in production, showing you how you can run the virtual participant framework both in your local environment, but also as deployed as a container using ECS Fargate and being able to invoke it via a Lambda function. So on the right hand side, this is my Windows environment. I have a local setup that will call the meeting, and I have a debug log showing so that it actually shows the recording of the meeting and sending it to Kinesis video stream. On the left side, this is the Lambda function. It effectively emulates the same. It emulates the same function as a curl. It's just sending the join and leave requests. At the bottom, you can see who's joining. So in this particular demo meeting, I have Chris and myself are the participants now. And on the right corner, these are the consumers that I'll run once the recording to the cloud and to Kinesis video stream starts. So with that, first, I want to show you the containerized version of this application running on ECS Fargate. So this is join. It's going to hit a base URL that the container is running on. And as soon as I send join with the right parameters, it should join as a Fargate virtual participant. So you can see that's the Fargate Zoomtopia. And at the same time, I can also have the local environment join as a second virtual participant. So this one should show up as a local virtual participant. So we have both virtual participants joining the same meeting. And now if I'm going to mute my local participant. If I start local recording using the host commands that I have, it should start sending the raw audio that's being captured from each user, both Chris and I, to Kinesis video stream. And I should be able to run two consumers that can show you the transcriptions that's coming from those Kinesis video streams. So with that, I'm going to allow local recording. This debug log will start streaming video out. And if I start my consumers, both Chris and I should be able to have our audio transcribed. So Chris, if you don't mind, maybe give me a couple of voice checks. 1, 2, 3.
Yep, testing. My name is Chris.
Fantastic. So Chris is on the left and I'm on the right. One other thing that I want to show, and you can see the call transcript is now showing up on the right side. is I want to give your attention that this call is actually having the personal identifiable information redacted. So if I ask Chris to give me his a random social security number, it should show it as a bracket SSN once the partial results are complete. So Chris, give me a social security number.
Yep, my social security number is 555-112234.
So what you can see is the partial results include the numbers, but once the transcription API gives the final result, it shows up as SSN, which is redacted that. So whether you send this to DynamoDB or downstream processing, the actual transcription that goes has this personal identifiable information redacted. So with that, I'm going to end the meeting. So again, I'll send the leave request to the local environment, and I can do the same thing with my Fargate task, and that should also have the Fargate one remove the meeting too. So with that, this demo is complete. We're going to show you a much more sophisticated version of this demo when we talk about log call analytics.
Thanks, Sina. So referencing the repository that Sina was talking about on GitHub, you can find the virtual orchestrator framework in a subdirectory on the GitHub open source repository. The virtual participant framework was implemented using the AWS Cloud Development Kit, also known as CDK. CDK enables developers to write infrastructure as code using commonly used higher level languages such as Python, TypeScript, and C#. Included in our TypeScript CDK application is a CDK pipeline, which also provides all the infrastructure and configuration necessary to set up a CI/CD pipeline within the demo. While you can configure the CDK application to use your own GitHub repo, the fastest way to get started is to create a code commit Git repository in your own AWS account. Commit the commits or commit the contents of the virtual orchestrator framework subdirectory and follow the README instructions. The README covers all the steps necessary to deploy the virtual orchestrator framework, including but not limited to securely storing all your Zoom app key and secret information in AWS Secrets Manager, building and publishing a Zoom Windows container, which includes the custom-built client application configured for use with AWS Kinesis video streams, initiating a Zoom call that will stream and store participant audio for downstream analysis and processing in your AWS account. Deployment of the virtual participant framework is initiated after the command CDK deploy is executed. This will kick off the first of the three phases provided by the framework: build, deploy, and command. In the build phase, a Windows container will be built using the Docker file from the repo, which includes the Zoom client application and dependencies such as GStreamer and the AWS and Kinesis video streams SDK for C++. Part of the container building pipeline includes the automatic provisioning and deprovisioning of an EC2 instance used to build a container image, which is published to a private ECR repository in the AWS account. In the deploy phase, we initialize an AWS Fargate task using the container image, which provisions a fully managed instance of the containerized application ready to join the Zoom call. Finally, in the command phase, our containerized application hosted in AWS Fargate is able to join a Zoom call through an API call powered by AWS Lambda. Once the containerized application has joined the call, the meeting host can enable local recording, and the virtual participant will successfully publish meeting audio Kinesis video streams. Similarly to joining a meeting, the virtual participant can also be dropped through an AWS Lambda API call or when the meeting has ended. To learn more about the framework details, visit the open source repository hosted on GitHub. Okay, that wraps up our deep dive with the virtual participant. Back to you, Sina.
Great, thanks, John. And as we saw in the demo, we covered a very basic use case of being able to transcribe, meeting audio from two participants with Amazon Transcribe. Next, I'm going to pass it to Chris, who's going to dive deep into a slightly more sophisticated use case based on our live call analytics solution to actually show how an agent assist solution can be baked into this virtual participant framework.
Thanks, Sina. Hi, everyone. Now let's talk about real-time call analytics and Agent Assist, which is part of the AWS Contact Center Intelligence Solutions. CCI solutions improve customer experience, boost agent productivity, and lower costs. Real-time analytics for Zoom meetings is based on live call analytics with Agent Assist, an open source project designed to get customers up and running quickly with analytics, artificial intelligence for meetings, all in real time. Its source code is available on GitHub, and it's quickly deployable in a few clicks with a CloudFormation template. Out of the box, it includes a customizable React user interface that will display transcriptions, Agent Assist responses, and meeting summaries, all in real time. Agents can log into the web user interface to see Agent Assist suggested responses, and supervisors can see how the calls are progressing. Live Call Analytics deploys an entire infrastructure to help you get going quickly without writing any code. Now let's watch a quick demo of LCA in action. Hello, thank you for calling Acme Bank. My name is Chris. How can I help you today?
Hi, I'm calling about my rewards card.
Excellent. Give me a second to look up your customer account. For verification purposes, can you please state your first name?
My first name is Sina.
One moment while we verify that the name matches our records. Perfect. Hi, Sina. How can I help you with your rewards card?
I was wondering, what is the cashback rate for this card?
I'm looking that up for you now. It won't take long. I see here that the rewards card has a 2% cashback rate on your everyday spending. Is there anything else I can help you with today?
Thanks, yes. Can I pay my card bill now while I'm on the phone?
Absolutely. We can process your payment over the phone. Give me a second to set that up. Can you please confirm the last 4 digits of your card number?
Yes, it's 1234.
Got it. 1234. So I can confirm that the card balance is $75.34. How much do you want to pay? There is a $50 minimum payment.
Yeah, I'll pay $50.
Okay, I'm entering a payment of $50. Do you want to pay from your checking account or your savings account?
My checking account.
Perfect. Your checking account. One moment, please. Great. So I've processed your payment of $50 from your checking account. Is there anything else I can help you with?
Nothing else just now. You've been a big help. Thank you so much.
No problem. I'm very glad to hear you say that. Well, thanks, Sina. We appreciate your business. Check out our website at acmebank.com to learn about all our other products, and feel free to call back if you have any additional questions. Have a great day.
Thanks. Bye.
Goodbye. The live call analytics demo you just saw is powered by AWS Contact Center Intelligence, again, a suite of solutions and services designed to derive insights and reduced operating costs by adding artificial intelligence and machine learning to your contact center. Use Amazon Transcribe to do real-time speech transcriptions, Amazon Comprehend for natural language processing, Amazon Kendra for intelligent search, and Amazon Lex for conversational AI and agent assist, and Amazon Poly to synthesize text into speech. Finally, we can also add Amazon Translate, our award-winning machine translation service. All of these capabilities are available to you without having to manage any servers or infrastructure. Simply start utilizing the APIs. We provide SDKs in many different programming languages for you to get started quickly. Finally, we have full documentation and example source code, such as Live Call Analytics and others, available to you on our website and on GitHub. Now let's take a quick look at the architecture of Live Call Analytics that utilizes these services. This architecture is designed around 2 main components that I've circled: the Zoom meeting, including the virtual participant on the left, and the language AI services, starting with Amazon Transcribe on the right. The agent can see real-time messages in the Live Call Analytics web portal on the bottom left. The architecture flows start with the virtual participant sending the meeting data to Kinesis video streams, as Sina demonstrated earlier. From here, an AWS Lambda function ingests the Kinesis video streams data on the AWS side, parsing out the audio and sending the audio streams to Amazon Transcribe. Transcribe returns the transcriptions in real time, and we use other AWS language AI services to generate agent assist responses. Finally, the agent assist responses, as well as the transcripts, are delivered back to the agent via AWS AppSync to the web portal, and they're also persisted in DynamoDB. All right, Sina, back to you.
I am so glad we were able to share the solution with you today and can't wait for you to try it. Let's look back at what we wanted to achieve. We set out to help developers build their own AI ML solutions with Zoom on top of AWS. Our goal building and evolving this solution is to make you productive, ease your operation burden, and keep your costs low. The LCA demo we presented was only a few weeks worth of work to integrate with Zoom once we had created the virtual participant framework. And we think you can do the same, if not better. This has been a wonderful partnership with Zoom, and we thank the Zoom team for their tireless effort helping us serve our joint customer and the developer community. Now, to get started, first, as I mentioned earlier, you need to have an AWS account, ideally with administrative access, so that you can try this out and build the solution on your developer environment. Then you need to sign up for a developer account using the Zoom app marketplace to register as a developer, get API keys, and also be able to download the Windows SDK. And once you have that, you just need to follow the README instructions on the repository hosted on GitHub and be able to stream audio from and run it and be able to stream audio end-to-end from a Zoom meeting all the way to transcriptions being available using Amazon Transcribe. Now, if you run into any issues or you want to talk to us, we encourage you to either file issues on GitHub or reach out to us using the Zoom Dev Forum on the Zoom site. Here are some of the resources that help you get started. The GitHub repo, there's multiple QR codes that you can reach for the GitHub repo, the Zoom Dev Forum, the app marketplace, and how to get started. We're so glad you could spend this time with us, and let's go build together. Thank you.